Swayamprabha. Digital India. Educated India.
Prandtl-Eckert by 2 y by L into 1 minus y by L. That is what we have. Now, if you plot y by L as the ordinate, t minus t naught by t1 minus t naught as the abscissa, Prandtl-Eckert becomes a parameter. So, if Prandtl-Eckert equal to 0 means there is no velocity of the plate, so it is a static thing. And then the heat transfer process is purely conduction, and please at this point assume T1 greater than T0 for our discussion purposes, T1 greater than T0. So, you will find when you plot this, when Prandtl is the fluid, Eckert equal to 0, there is heat transfer from top plate to the bottom plate, because T1 is higher than T0. That you can easily make out. That profile will tell you. Now, as you now put in some value for Prandtl-Eckert starting greater than 0, 0.5, 1, 1.5, 2, 3, 4, 5, 6, something interesting is happening. That is why I take up this problem. I will just do my bit and go. At Prandtl-Eckert equal to 2, rather I would say if Prandtl-Eckert greater than 2, there is something very interesting happening to the temperature profile. Now, when you draw this temperature profile, you will take the abscissa as theta from 0 to 1, and of course y by L 0 to 1. So, one would like to think that all the profiles would be within this 0 to 1, 0 to 1 thing, but when you go beyond Prandtl-Eckert equal to 2, suddenly you will see the temperature profile extending outside theta equal to 1, number 1. Number 2, not only that, when we say the top plate is at T1, you know what it means, it is held at T1, it is artificially deliberately held. So, if there is some heat transfer into that, you are taking away that heat to hold it, that is what it means, it will not go beyond that. So, T1 is held constant, the temperature profile is extended beyond 1, that means the temperature there is now higher than the temperature of the plate T1. What it means is, although you are holding the temperature T1 greater than T0, you are holding it at certain Prandtl-Eckert number, meaning at certain U1 value, the profile extends, temperature profile extends beyond the theta 1, but you have to bring that profile back to that one point. Now, you see the gradient has changed its direction. Originally the gradient was like this for Prandtl-Eckert equal to 0, gradually when you increase the Prandtl-Eckert it became at 2, it became vertical at y equal to L, and when you went beyond Prandtl-Eckert equal to 2, the profile is changing. That means the direction of the heat flow is changing. So, what does it mean? Although you are holding T1 and T2 constant deliberately, T1 being greater than T naught, at a value of Prandtl-Eckert equal to just beyond 2, heat has now started flowing into the top plate rather than from the top plate to the fluid. That means there is a heat reversal has happened, heat flow reversal has happened. This is something now which is coming out, because coming out of our Couette flow, because we took the viscous dissipation term into consideration, du by dy whole square. We did not neglect it, we said yeah, du by dy may be important, d by dx we neglected, d by dz all those we neglected. When we have taken a problem where du by dy is finite and it should be considered, you find now beyond a certain value of u1, heat is started flowing into the upper plate. The question one, this only if you plot you will understand. Then you think what is happening to the physics of the problem. Now, the answer is that somehow this increasing velocity, increasing Eckert number, increasing velocity has generated heat in the system. That heat has caused the fluid temperature to rise. That rise in fluid temperature beyond the T1 value is what is the cause of heat transfer into the T1. Therefore, increasing velocities are finally the root of at this phenomenon of heat generation within the fluid and therefore heat transfer to the top plate. This is happening. This phenomenon of heat generation within the flow because of U1 is viscous dissipation. Actually it is viscous heat dissipation, viscous energy dissipation. Now this viscous dissipation is not simply kinetic energy, it is not simply U1 square, it is actually mu. If you look at the energy term, energy equation, mu du by dy whole square, mu is always present. So it is a combination of the viscosity and the velocity gradient. So it depends upon what are the values of these two. Mu can be extremely high, du by dy can be very small, viscous dissipation is important. When is mu very high? For oils. So when there is a oil involved, even small du by dys can generate enough viscous dissipation. On the other hand, if you go to low viscosity fluids, typically air is extremely small, but even under those conditions, if du by dy is very large, mu into du by dy whole square will be considerable. So for low viscosity fluids, high velocity gradients will cause viscous, there is heat generation and therefore heat transfer. For high viscosity fluids, even small gradients will lead to the same effect. I am trying to make an important point here. It is not simply viscosity that counts, it is not simply the velocity gradient, it is a combination of these two which brings in a very important physical phenomenon into the system where heat is being generated. When heat is generated, it has to escape somewhere, it tries to go towards the plates, and that can happen only when the temperature of the fluid itself is very high, higher than these two plates. That is what you see when you plot these temperature profiles. You can go up to 4, 6 and 8, even 10. So viscous heat generation has now caused heat flow reversal at the top wall, number 1. If there is a heat the temperature profile reversal, there should be a maximum for that profile. Please find out what the maximum temperature is. This is all a case T1 greater than T0 only we are talking about. What is the maximum temperature and at what location it occurs, please find out. Now this is purely by plotting the profiles you can make out. How else can you find out that there is a dt by dy equal to 0 at the top wall? Please look at the file. Can you find out by an analysis what is the value of Prandtl-Eckert equal to 2? If you plot it, you will know that, but derive an expression for the value of Prandtl-Eckert equal to 2 when dt by dy is 0 at the wall. That is when the change of direction takes place. So you have the temperature profile is there, Ty, differentiate that dt by dy, at y equal to L you put 0 and obtain Prandtl-Eckert equal to 2. That is what I am telling you to do. You can get it through the profile if you plot, which you have not plotted, but at least analytically find out from the T equation at what value of Prandtl-Eckert is dt by dy equal to 0, 3 or 4 steps. Please obtain Prandtl-Eckert equal to 2 as this critical number beyond which heat gets transferred into the top wall, although T1 is greater than T0. We emphasize this point simply because there is a mindset amongst all of us generally that as long as T1 is greater than T0, it should always flow, the heat should always flow from T1 to T0. But what this problem tells you is, no, that is not right, your mindset is not right. There is what is called as a viscous dissipation that is possible. It is possible for low viscosity fluids at high velocity gradients and high viscosity fluids at low velocity gradients. Heat is generated because of this viscous shear. That shear force, which depends upon the kinetic energy, is converted into heat. That heat is now trying to escape. If the temperature of the fluid goes beyond the T1 temperature of the top plate, there is heat transfer into the T1. Do not always look at the physical model and say T1, heat transfer will be always from T1 to T0. That is what it says. This is the effect of viscous dissipation, importance of mu and du by dy. Always look at mu du by dy, not mu alone, not du by dy alone. Please obtain that as Prandtl equal to 2, Prandtl-Eckert equal to 2. Also, where does the y maximum occur? T maximum occur. This is again dt by dy at 0. You have to find out where dt by dy becomes 0. and please obtain this. I am really not going to write anything on the board. I am a little unhappy with nothing being done by you. You are all intelligent people, please do this yourself. I will give you the final y max. This is where the T max occurs, in this case of T1 greater than T0. So take the temperature equation, differentiate it dt by dy, and find out where this is equal to 0, that is the maximum point. Please obtain this following expression: y maximum is equal to, I am going to dictate, note down if you are interested, y maximum is equal to k by mu u1 squared. Again and again this mu u1 squared k combination comes in all this problem. Mu u1 squared by 2k, k, 2kl, mu u1 squared. You can look at the term mu viscosity, u1 squared kinetic energy. Y max equal to k by mu u1 square into T1 minus T0, this is the imposed temperature difference, plus why is this half, plus half not plus half, it should be plus L by 2. Y max equal to k by mu u1 square into T1 minus T0 plus L by 2. I think L you should get. And one thing we can check here, if T1 equal to T0, equal temperatures, where will the maximum occur? So check that here from this expression. If T1 equal to T0, Y maximum will be L by 2, and find out what that temperature is. Okay, do that. Now I will ask a question. If T1 equal to T0, equal temperatures occurred equal to 0, there is no heat transfer at all. Its entire fluid body is at T0, whatever equal temperature, let us say T0 T0. The moment you introduce the plate velocity, and depending upon that, now heat transfer comes into picture. A non-heat transfer problem, an adiabatic problem, you are converting into it is converting itself into a heat transfer problem simply because of the imposed flow that you have created. You have not used any pump, an imposed flow because of the movement of the plate that you have imposed actually. So now there is a viscous generation that heats up the fluid. Only thing is, it is doing it symmetrically, because both the plates are at the same temperature. The heat that is generated has to go in these two directions. You will find a nice symmetric temperature profile, y equal to 0, T equal to T0, y equal to L also T equal to T0, you can call it or TL, but both of them are equal, and there is a parabolic temperature profile with a maximum at L by 2. Find out what that maximum. I have asked you to do this also for oils. You will find these temperatures could be very high. For air it does not matter, but this is taken for our lubrication problems. T max is the most important physically significant thing coming to us from Couette flow. In the case of lubrication films, what would be the temperature of the oil film that you will attain at various U1? Why is it important? Higher the temperature for liquids, what happens to the viscosity for liquids? Will it increase or decrease for higher temperature? Decrease. That will destroy the lubrication characteristic of that particular thing. So we want to keep the maximum temperatures within a certain limit, therefore this comes in. So you will find, by looking at physical situations, you should be able to formulate your own problem. When you look at a heat transfer problem, you should be able to identify whether it is conduction, convection, radiation, what are therefore the important parameters coming into picture, what is the physical model. All that you have to do, it is not simply that this is given as something very specific. What it tells you, what you should understand is, you look at the heat transfer situation, think about it, write down the physical model and find out what are the parameters, find out how heat is transferred and what variables control the heat transfer. Now I have also asked you to look at calculate heat transfer at the lower wall, both lower wall and upper wall. You have the temperature profile. Okay, how do you write down a small expression for heat transfer at the lower wall? How do you rather calculate it from the temperature profile? How QW equal to minus K at, have you done that? Y equal to 0. Now can you tell me therefore what is the final expression for Q at Y equal to 0? This is very important. After all, temperature differences are there, thermal conductivity is there, L is there. This I will give you 3 minutes to do this, please. I will just give you a hint, QW or whatever is equal to K by L into, give me what is there in the brackets, K by L, it should be of the order of K dt by dx. So, K by L you take, give me what you get in the brackets in terms of Prandtl number. Q at the bottom wall equal to K by L multiplied by something in the brackets in terms of Prandtl number. Yeah, tell me. K by L, I have taken it outside the bracket. In the brackets, you tell me. Further simplify it here. There is no more L. If you have taken L outside the bracket, there will be no more L. K by L has come out. Give me the thing in the bracket. Yeah, anybody else? What is it? Okay, okay. There are several ways of how you can put it. Can you please do this? See whether you can put it in this form. Can you tell me here now what I can write? Huh? Then this is simple conduction equation, as you can see, K by L T naught minus T1. Please see whether you can get this into this form. Slight manipulation. K by L, you got it? Anybody has got it? K by L. Now, I hope you have got it. Now, look at this expression. This is the Q at bottom wall. So, there is usually one would think K by L into T naught minus T1, but now we know that is possible only when Eckert number equal to 0. So, fine. And if T1 is greater than T naught, you will get a directions you will get, you minus and all that. But you see from this expression, the driving temperature difference when viscous dissipation exists is not simply T naught minus T1, but it is T naught minus, you take this together, T1 plus Prandtl U1 squared by 2 Cp. Look at Prandtl U1 squared by 2 Cp. Obviously, the units of that term must be temperature, it has to be temperature. So, this is the heat flow at the bottom wall. Mark it, leave it, we will go to the next step, we will come back to this equation later. So, when T1 is greater than T0, both the plates are at some temperature controlled, the heat flow at the bottom wall is equal to K by L into T naught minus bracket T1 plus Prandtl U1 squared, leave it at that. Now, take up the next problem. Now, you have a Couette flow, you have done this, hopefully you have done this in your exam. You have a Couette flow, the bottom plate is insulated. Get me the temperature of the bottom wall. The insulated wall, it has some temperature. There is some temperature attained by the insulated wall. What is that temperature? Again, go to the same temperature equation is the same. That this now another thing you will learn here is temperature equation is the same, different boundary conditions, T1 greater than T0, T1 equal to T0, T0 greater than T1, dt by dy 0 at wall. All these will give you different information and of course answers, but more than that information that you can cull out of it. One, we have now seen that viscous dissipation is important beyond a certain Prandtl Eckert, and it has a tendency to make the heat reverse even though the temperature is high, we have said that. Now heat transfer at the bottom wall, you got it as K by L into T naught minus of T1 plus Prandtl U1 squared by 2 Cp. Keep at the side. Take a new case where the same Couette flow, bottom plate is insulated. Get me a simple expression for the temperature of the bottom wall. Y equal to 0, dt by dy is 0, y equal to L, T equal to T1, same thing. The two boundary conditions, two constants. Get me the temperature for the bottom wall, which is actually dt by dy at y equal to 0. A very simple expression. You got it? Tell me T at y equal to 0 is what? Yeah. Can you give it in terms of Prandtl number? Yes, little man. Whenever you find mu and k, you put a Cp there, make it into Prandtl, divide the other thing by multiply, divide by Cp. This is okay, no problem with it. It's permitted. That's why it should be easier for them. Yeah. The temperature profile, y equal to 0, dt by dy is 0, y equal to L, T equal to T1. Tell me if you have completed. If you have made a mistake, it does not matter. Tell me. This is okay. Tell me now. Any one of you know. Start with the temperature term here. T 1 plus Prandtl not rho. Now, what is the problem you have taken? Couette flow with y equal to 0, dt by dy equal to 0. When I say dt by dy equal to 0, what is? Can you use a word to describe that surface? It is a dt by dy equal to 0 means what? It is a adiabatic. It is an insulated surface, it is an adiabatic surface. That means the temperature at Ty equal to what you have got is actually T adiabatic wall or T ad whatever. So, in an insulated condition, you have now the temperature. Now, and please see, it is always higher than T1. We did not specify the temperature as T0, we specified an insulated boundary condition. Then when you got it actually in terms of the other variables, you found the at y equal to 0, which we now call the adiabatic wall temperature, not the adiabatic temperature, adiabatic wall temperature or insulated wall temperature. You found T1 plus something which depends upon U1, of course the fluid also, very important. Leave it. Now, go to the previous case where you found the heat transfer at the bottom wall. Look at that. Heat transfer at the bottom wall, QW equal to K by L multiplied by T naught minus, you are getting this, but that was not adiabatic wall, that was T y equal to 0, T equal to T0. So, for the case of a non-adiabatic situation here, yeah. So, actually what now I can write? I can actually write it as adiabatic. For the non-adiabatic case, I can still invoke the adiabatic wall temperature concept now, although it is not adiabatic. I am communicating here. The T1 not equal to T naught case is not adiabatic, but when you calculate the rate of heat transfer at the bottom wall, you are getting a combination of parameters which happen to be give you the adiabatic wall temperature. How do I know it is the adiabatic wall temperature? That is what you did just now. Putting dt by dy at y equal to 0, you said the temperature that is attained by the insulated wall is this, but this happens to be the same as this. That means, ladies and gentlemen, even in a non-insulating or non-adiabatic wall condition, now what is this? This is the equation for heat transfer. The driving force, driving temperature difference is not simply the imposed T naught minus T1, but it is a imaginary temperature difference, the driving potential, which has now adiabatic wall temperature into it. If you say, sir, there is no adiabatic wall, yes, there is no adiabatic wall. So, this is a concept of the adiabatic wall is coming into the non-adiabatic thing, meaning the first thing that now when we got this expression, we did not use the term anywhere that is a high velocity flow. We have not used it. We did not say it is high velocity flow. We said, we went on saying Prandtl Eckert. What is the value of Prandtl Eckert? Meaning the effect of the Prandtl number and the velocity is coming into picture. We simply did not say high velocity flow, because you have done high velocity flow in forced convection. High velocity flow, you said du by dy, Eckert number you said. Now, I did not say high velocity. I simply said we will take mu by k du by dy whole squared into consideration. Let us see what happens. Now, in that situation, the actual analysis is telling me the heat transfer at the lower wall for a certain Prandtl number, for a certain du by dy is not simply k by l into T naught minus T1, but it is k by l into T naught minus a new temperature, which is T1 plus Prandtl U1 squared by 2 Cp. Then you found it is adiabatic. So, what it means is, in all such situations, and it is true for normal convective situations, there is always a velocity of the flow. Either the flow is there is a velocity of the flow, or in this case there is a velocity of the plane, because convection is relative velocity. Whenever there is relative velocity, therefore, that is in convection, the correct driving temperature potential is this, and not simply the temperature difference that you see on paper. Therefore, for all convection cases, the first thing that you have to do is calculate TAW, even if it is not a adiabatic case. That is the right temperature. The moment there is U1 there, the question is U1 squared by 2 Cp is there. It may be small, large, very large, that is a different matter, but it is there. U1 is not 0. The moment U1 has come into the picture, where it is a Couette flow and then you go to the boundary layer flow, there is a kinetic energy, there is a viscosity, therefore, there is a viscous dissipation. The question is it important? How important? Now, when you do not know what it is, what you should do is take this expression for calculation. If that you have understood, the next question is, how do I get the T adiabatic wall temperature? Go one step ahead now. Look at this T adiabatic now is equal to, what is it? Prandtl U1 T1 plus, okay. T1 plus, we will make a small again manipulation here. Bring T1 to the left hand side. So, TAW minus T1 divide by U1 square by 2Cp. Can you tell me what it was now that you have done the high velocity flow? You have done the high velocity plate. Arvind? Yeah. What is this term in high velocity flow? No, what is it called? I'll put a symbol for this. Tell me. In high velocity flow, you got a very similar expression. You already knew about adiabatic wall temperature earlier actually. TAW minus T1 divided by U1 square by 2Cp. I will give you a hint. Before I left in the last class, I said, can you compare the Couette flow to something else which you know? That is a boundary layer flow, isn't it? Now, what is T1 corresponding to then? In boundary layer flow, what does T1 correspond to? And U1 corresponds to? So, suppose you put TAW minus T infinity here, U infinity by 2Cp. Now, do you recollect what it was? No, standard is H by rho infinity Cp. Yeah, look into the notes if you have. I want you to give me the name of this term. Maybe you are more familiar with that flat plate problem. Therefore, in this I am replacing T1 by T infinity, U1 by U infinity. That is a boundary layer problem. It is that the way of looking at it is right, but what you get on the right hand side will be different. But what is this term called? TAW minus T infinity divided by U infinity squared by 2Cp. Please find out U infinity by 2Cp is a temperature term, therefore it is non-dimensional. You want me to give you a hint beyond that? You do not have the notes, earlier notes? High velocity boundary layer flow with air. What is it called? Now, you thought recovery factor was only in high velocity boundary layer flow. Now, I am giving the recovery factor in a simple Couette flow, which you have solved by hand. Complete set of Navier-Stokes equations is not a boundary layer flow, it is a parallel flow. You took the governing energy equation, including a term which you didn't know what it was, but du by du whole squared it did not cancel out. So, you took that into consideration. Then when you take the temperature profile and put the various boundary conditions, you are getting so much of information. First thing you got was the cut number. Then we know now there is a heat reversal at the wall, even though T1 is greater than the bottom temperature. That is because of viscous generation, and there is therefore some critical value where viscous heat comes into picture. That you found out, you should find out Prandtl cut equal to 2 by dt by dy at that equal to 0. Now, you go one step beyond. You find that the non-adiabatic case, the bottom wall temperature is something which is very similar, for which you need a temperature from an insulated boundary condition, which is the insulated or adiabatic wall temperature. So, you take the adiabatic wall temperature term, put it into the non-adiabatic thing, that is the right driving equation for convection, is what I am now trying to tell you. And now, if you go further, now I asked you T infinity unity, now I will come back to TAW minus T1, because it is a Couette flow situation, there is no infinity here. This is called the recovery factor. And what is the recovery factor in this case? This is equal to, from this expression, so much comes out of this problem, you know. Why is it called recovery factor? Recovery factor is recovering something. Something is being recovered. What is being recovered? You can guess. Huh? Don't say heat loss. The heat that is generated by viscous dissipation, that is being recovered. In the case of the adiabatic wall, where is it being recovered? If you see, it is going to the, by the way, what is the max, I will just go back, what is the maximum temperature in the adiabatic case and where does it occur? I think I have asked you this question. Where is the adiabatic temperature, maximum temperature, where does it occur? You know the T1 T0 profile you have drawn. So T1 T0 is held constant, so nothing can happen. The maximum temperature occurred in the fluid. T1 equal to T0, same thing. T max occurs in the fluid at y equal to L by 2. In the adiabatic case, which is the maximum temperature? Where? Yeah, at the wall itself. Yeah, so draw the profile. At y equal to 0, that is the maximum temperature. How it has come about? Some of the heat that is generated is been recovered at the plate. This may or may not be the very right physical interpretation, but this gives us an idea. The heat that was generated by friction has been recovered by the system itself. It has not let it go as a loss. If it is a loss, well, still the insulated surface would have some temperature, maybe it is slightly lower, but when it has recovered, taken the heat and separate part of it. In insulated case, there is no heat loss from the plate, dt by dy is there, but at that point whatever it has absorbed, it has raised its temperature. So in an insulated boundary conditions case, the insulated plate temperature is the highest, and therefore you can draw the profile. I want all of you to draw the Couette flow, draw the profiles for T1 greater than T0 case, T1 equal to T0 case and the adiabatic case. See the temperature profiles, how they change. Okay. Now you go beyond that. So we are saying here the frictional heat is being recovered, therefore it is a recovery factor. Now we will go to the next step. So what is the recovery factor equal to? Can you tell me from your notes what was the recovery factor for that particular case that you? Huh? So what is the value of the recovery factor for the high velocity laminar boundary layer flow, whatever you have done, laminar or turbulent? Laminar, I think. That R value, what is it? You got the R somewhere there in your notes? So R, there should be a relationship. R equal to what? Suppose I want to calculate. You got TAW minus T infinity divided by U infinity by 2 Cp equal to R. That R equal to what for that particular situation? I am sure you have that value there. From your notes. What will in terms of what you will find the value of R at least? No, you must have written it down. You got the definition of R in your class notes? Come on, I shouldn't be asking you so many questions here. You said recovery factor, fine. So there is an expression for recovery factor. I am asking you what is the value of that in that particular case. It is a laminar flow flat plate case. Find out, it should be there. We will go further. I wanted to bring to the point here that R is a function of Prandtl number only in terms of number, but it changes from situation to situation in terms of the geometry and the flow. So a flat plate laminar problem has a certain recovery factor, which is a function of Prandtl number. A flat plate turbulent flow has its own recovery factor, which is a function of Prandtl number. A Couette flow, we did not specify the fluid here, but fluid is the Prandtl number. So for the Couette flow, the recovery factor, it does not matter whether it is adiabatic or not, that is not the point at all. Recovery factor value is equal to Prandtl. So if you know the Prandtl number, half the solution is known. Now I do not know whether you have missed, for laminar boundary layer it should be a Prandtl power half or something. Laminar high velocity, no you have missed it, you should be there somewhere there, it should be square root of Prandtl number. This is very important for us to know that the recovery factor has a value which is some factor, I do not want to say function, yeah okay, function of Prandtl number, Prandtl power 1 half root 1/3 or whatever. In the case of Couette flow it is equal to Prandtl number, that is all. For high velocity laminar boundary flow with air it is I think Prandtl power half, you please check. For turbulent flow it will be Prandtl 1/3 I think, please check it out. This is very important, two aspects. One, you should know that recovery factor is a function of Prandtl number and also how much it is, because one is a physical significant recovery. Now, so tell me, when you want to solve a problem for your, how does this help you, this expression? What is it that you know, what is it that you do not know in this expression? This is expression to calculate the adiabatic wall temperature, because you always know the fluid, is there air or for us you know air, oil, it could be water, it does not matter at all. So the moment you know what is the fluid, of course you know the plate velocity, this is given, plate velocity, plate temperature, TAW is known. The moment TAW is known, you go to the heat transfer equation. Do not simply put T0 minus T1, that is what I am trying to convey to you. Same thing in the case of laminar boundary layer flow. Usually what is the Newton's law of cooling? Q is equal to HA delta T, delta T is TW minus T infinity. I am saying do not do that, take TW minus T adiabatic, you do not have to worry. Now T adiabatic has U1 squared, all it simply means is if U1 is small this is negligible, if U1 is considerable that will be important. It could be a rise of 0.001 degree centigrade when U1 is small, but it is there, you may neglect it, but it can never be 0. Viscous dissipation is 0 only when U1 equal to 0, but then we do not talk about convection at all in this case. So the moment there is a U1 that is coming into picture, fluid velocity, there is kinetic energy, there is a viscosity, there is a velocity gradient, therefore mu du by dy whole square becomes important. That comes from tau w equal to mu du by dy. So viscous shear leads to heat generation heats up the fluid, and the temperatures in the fluid will be slightly higher than what actually the T infinity, but it may be negligible. If T infinity is 150 degrees centigrade and the viscous dissipation has increased at 0.1 degree, you do not care. But if T1 is 150 degrees centigrade and viscous dissipation has increased by 40 degrees centigrade, now on what does that depend, either 0.1 or 40? Two things, Prandtl number, the fluid, and the velocity gradient. How? Eckert number, Prandtl Eckert number. So when we want to calculate the rate of heat transfer in convection, in any situation, this is an example, the same thing you can do in the laminar. Here it very clearly says, do not worry about what U1 and T1 are there, get the adiabatic wall temperature, use this expression, T0 is actually TW in a way, our old thing, and immediately you have the heat transfer coming into picture. So we do this Couette flow generally in the beginning of the laminar flows. We never said laminar, we did not say turbulent because it is all for laminar. We wrote the expressions for laminar. We do this therefore to first of all understand the procedure of solution of a convective heat transfer problem, starting from the physical model. I will never, I say this very often, you have to start with the physical model, ad nausea as I say, physical model, mathematical model, simplification of the equations if they are very complex, and neither equations are complex. Then take the simplified version. So in a boundary layer flow it can be Prandtl equations, but in this case there is no name given to those 4 equations, dw, d square u by dy, what name, there is no name, but you please look at them. It is like in conduction, what is the simplest expression for conduction? d square t by dy square equal to 0. You can't get anything simpler than that with two boundary conditions. Similarly, you have here d square u by dy square equal to 0, dw by dy square equal to 0. Y momentum has taken care, energy equation, we wrote everything. We said there is no heat generation, so we did not say there is no viscous dissipation purposely, so that we wanted to study because it has du by dy. Now in this, after that you have to solve. You do not have to rush to the computer, big fluent code, you can do it by hand. This is the only problem and the corresponding Poisson problem which you can do by hand with three different boundary conditions, T1 greater than 0, T1 equal to T0, I want you to do that, and a boundary condition at the insulated boundary condition. You get different temperature profiles, but importantly you find a lot of physics, the effect of viscous dissipation, the possibility that the heat transfer can go to a temperature which is higher than the other temperature in the system, simply because the fluid has increases temperature. A practical application in lubrications or anywhere where oil is involved as a lubricant, it loses its viscosity at this higher temperature. That is the important thing. So you have to find out what is the. That is why the gaps are given as 3 mm, 4 mm. Otherwise it is not a duct kind of a thing. And then you come the new non-dimensional term which is the Eckert number, which you never thought you would do that. You did not say it is a high velocity problem, but it came in Eckert number. Then when you temperature profiles were done, you got the heat reversal. Then you go to the adiabatic wall temperature, there you find you can get adiabatic wall temperature expression, but that is exactly is what appears in the non-adiabatic case. Therefore in the non-adiabatic case, even for you to calculate the heat transfer, first calculate the adiabatic wall temperature. That can be obtained through the definition of a recovery factor, which is nothing but TAW minus T1 by U1 square by 2 Cp, which is a recovery factor. In this particular case, it has a definite value which is equal to the Prandtl number. If it is oil, it is 1000, if it is air, it is 0.72. And immediately you know the effects will not be very high in the case of air, but it will be extremely high in the case of oil. There itself, the Prandtl number effect is simply hitting you in the eye actually. And therefore, when you want to find out the rate of heat transfer in any convection problem, you say right thing to do fundamentally is calculate the adiabatic wall temperature, which is non-existent, which is an imaginary thing. It is as if there is a adiabatic wall temperature. There is no adiabatic wall temperature in our normal our cases. This is very important for you to understand, because students will always ask, sir, why do we calculate the adiabatic wall temperature? There is no. It simply so happens, the physics tells you, when you have this non-adiabatic equation, there is a term which is nothing but the adiabatic wall temperature. So you say there is an imaginary adiabatic wall temperature, imaginary temperature which is equal to adiabatic wall. Once you put that in, that is the right equation for heat transfer, and that is a function of Prandtl number which comes through a recovery factor. Recovery simply means the frictional heat that is being generated is being recovered as much as possible within the system. That is all it means. So for you to solve this problem for heat transfer in all convection system, get the adiabatic wall temperature through the recovery factor, which is simply a function of Prandtl number. We can actually plot all this as a function of Prandtl and R for various flows, and go back and calculate the rate of heat transfer. All these new ideas, physics of the problem, how to solve the convection equation, how to put in the boundary conditions and actually solve. Now if you take a complex Navier-Stokes equation, you won't do this, you will go to a code that you won't know how it is done. You have now integrated every equation, the temperature equation twice every time to get the two constants depending upon the two boundary conditions. So the whole thing about convection is encapsulated in this Couette problem. If you know this problem completely, you can play with any equation. Even if you go to the code, at least you know what is happening. How did this come up? How did the rate of heat transfer calculated? Q is equal to minus k dt by dy. That is why in the beginning stage I said physics wise, I want for my heat transfer dt by dy at y equal to 0. For me to get that, I have to have the entire temperature profile. For you to have the temperature profile, you have to have the energy equation along with the boundary conditions, and that comes from nature, which is the first law of thermodynamics. So from nature to rate of heat transfer in an adiabatic or a non-adiabatic situation, you can understand, provided you actually do the calculations by hand, not by a computer, put Prandtl, Eckert various values, plot it. Earlier we used to have these graph sheets on which we used to plot, and as the plot we are plotting, the whole thing comes visually. You don't have to accept what I say or what the computer says. You do it by hand. This is the only problem which you can do by hand and see the solution as I say, coming out because of you are churning all the information, mathematical information, physics information, you integrate these together to calculate the rate of it.